When we think about molecules, we're usually thinking about a single, isolated molecule. On the other hand, when we do experiments, we're normally dealing with an ensemble of molecules. And this necessarily means that molecular properties that we're interested in are going to be averaged somehow over this ensemble, and in the worst case, the measurements we're making may not even be sensitive to the properties we're interested in.
Perhaps the most obvious example is the spatial alignment of the molecular axes. In the laboratory, the ensemble is isotropic, so there is no relation between the molecular and laboratory frames of reference. Any measurement we make is averaged over all molecular alignments. One way of beating this averaging is to create alignment in the molecular ensemble via the use of an intense infrared laser field. In the impulsive case, where the laser pulse is short relative to molecular rotations, a broad rotational wave packet can be prepared in the ensemble. This creates a temporally varying spatial alignment. We can describe this alignment in terms of the spatial probability distribution of the molecular axes, as shown here. By choosing to probe the ensemble at different times, we can therefore probe different ensemble alignments. In a limiting case of perfect alignment, we can even approach a molecular frame measurement. There are many ways to probe aligned ensembles, but perhaps the most popular and general technique is via ionization. In this case, a photoelectron is created, and the time-dependent yield and angular distribution can be measured. However, the coupling between the observable and the ensemble rotational wave packet is pretty complicated, and this complexity is often ignored. In general, this is a problem, since without a deep understanding of this coupling, experimental results cannot be correctly interpreted. Even a relatively fundamental task such as optimizing and quantifying the alignment achieved experimentally becomes impossible, let alone more complex tasks such as measuring molecular frame properties. In this work, we detail the fundamentals of a geometric treatment of aligned ensembles, and their coupling via single and multi-photon ionization for angle integrated, polarization resolved, and angle resolved measurements. The theory is illustrated with extensive numerical examples, both to visualize the consequences of this coupling in specific limiting cases, and to highlight some of the general phenomena which observe from a geometric treatment of the aligned ensemble uncoupled observables. Although the details are specific to ionization measurements, many of these general conclusions are applicable to other methods which probe aligned ensembles. Consequently, this work should be of interest to any researchers interested in molecular alignment or measuring molecular frame properties and dynamics.